Hello students, today we are going to learn about asynchronous digital counters. I will explain you the theory by the help of a lucid animation. So I will particularly talk about that how this digital counter works to understand the physical working of the counter. So before proceeding, I will take an example that you would have used this pulse oximeter device, a medical device, or you might be knowing about this, that in case you put the finger inside this device, it can tell you that with how many beats per minute your heart is pumping the blood. Okay, so how this pulse oximeter works? See, when heart pumps the blood, it pumps intermittently. So when it pumps intermittently, every part of our body beats. Okay, however, we cannot feel it at every portion of our body. We cannot feel it, but the sensor of this machine can sense those minute pulses, feeble pulses. Okay, so what happens? The pulse oximeter changes those minute pulses of finger into electrical clock signals, discrete clock signals. Now, what is digital counter? A digital counter counts those clock signals, the clock signals which are converted from those pulses, counts those clock signals and sends the data to the arithmetic logic unit of the device. Over there, the arithmetic logic unit divides the number of clock signals with the amount of time, say per minute, and it tells that with how many beats per minute your heart is pumping the blood. Okay, so coming to the definition, a digital counter is a device, is an electronic device which can count the number of clock signals which is fed to that machine. Okay, so before proceeding, I will take a brief demonstration of a JK master slave flip flop. In case you want the details that how this JK master flip flop works and what is JK master flip flop, then the link is over here. Right now I will talk in brief about this, because to learn about digital counters, the knowledge of this JK master slave flip flop is a must. Okay, so in totality what it does, see, this is the JK master slave flip flop which has two inputs, J and K. And for digital counters, the J and K both are kept 1. High input are provided to J and K. These are the outputs Q and Q naught. Both are invert of each other. Means if Q is 0, Q naught is 1. If Q naught is 0, Q is 1, like this. And there is one more input that is called as clock signal or enable input. Okay, so right now it is 0. Now in this condition, if this clock signal goes from 0 to 1, initially it was 0, now 0 to 1, nothing change will occur in the output. Now in case this comes back to 0, one complete cycle is rendered to this flip flop. So 0 to 1 and again back to 0, now the outputs are changed. You can see initially it was 0 1 and now it is 1 0. So in case to this clock input, if a complete clock signal is provided, means 0 to 1 and then again 0 back, then the outputs will be changed. Okay, in case one more complete clock signal is provided to it, now again the outputs will be changed from 1 0 to 0 1. You can see. Now I'll take an example of 3-bit digital counter, asynchronous. So what is its architecture? You can see that there are 3 flip flops, yellow, purple and red. Okay, and these are the inputs from right to left, J and K. So all the flip flops, the J and K are kept 1, as I told. These are the outputs Q and Q naught, Q and Q naught, Q and Q naught. And what we see, that the output of one flip flop is actually input of another. Yellow flip flop's output, that is Q, is input clock signal to the purple flip flop, and the output of this purple flip flop, that is again Q, is a clock signal to the red flip flop, like this. So over here I am taking an example of 3-bit digital counter. Now why it is called as, this system is called as asynchronous digital counters? Reason being that the clock signal is provided only to the first flip flop. Okay, the rest of the flip flops are actually receiving the clock signals as an output of the previous flip flops. Okay, this is the reason it is called as asynchronous counter. In synchronous counter, what happens, which I am not telling right now, all the flip flops are clocked simultaneously. So for that I will make another lecture. Right now we are studying asynchronous digital counters. Now we are bothered with only one output, means what is the value of Q at a time. So over here I am showing, and the Q naught is not required for counting the clock signals. Q naught is not required, so they are left as it is. Only Qs are required, like this. So right now all the Q outputs of the flip flops are 0. Okay, and the decimal equivalent of 0 0 0, in case I take it as binary 0 0 0, then decimal equivalent is also 0. Okay, now suppose one complete pulse is provided to this first flip flop, like this, 0 to 1 and then again back 0. So what will happen? If one complete pulse is provided, then this Q will change into 1, because one complete pulse is required to change the outputs. Okay. Now this is the input to this purple flip-flop. So the output of this purple flip-flop will not change. Reason being that the output of this yellow flip-flop has been changed from 0 to 1. This is not complete cycle input to this purple flip-flop. For changes in the output, one complete cycle 0 to 1 and again back 0 is required. So the output of this purple flip-flop will not change, and in case there is no output change for this purple flip-flop, red flip-flop will also not change. Now what is the decimal equivalent of 001? It is 1, we know. Okay. Now one more complete clock signal is provided like this. Now the output of this yellow flip-flop again comes back to 0. Okay. So initially it was 0, 0 to 1 and again back 0. So one complete pulse is provided to this purple flip-flop. In this case, the output of this purple flip-flop will change from 0 to 1. Okay. But this red flip-flop output will not change, because again for this red flip-flop it is half pulse, 0 to 1 only. So what is the decimal equivalent of 010? It is 2. Now one more pulse is arriving. This Q will change from 0 to 1. So for purple, it is only half pulse, no change will occur. And what is decimal equivalent of 011? It is 3. Now one more pulse. So 1 again changes to 0. So for this purple flip-flop, one complete pulse has been provided. So the output of this purple flip-flop will change from 1 to 0. So in this case, this red flip-flop output will change, because the purple flip-flop output has been converted from 0 to 1 and then 0 back. So one complete pulse is provided to this red flip-flop. So you can see that output of this red flip-flop now has been changed. So 100, what is the decimal equivalent? It is 4. Now one more pulse. So again one complete pulse. So the output of this yellow flip-flop is changing to 1. This is half pulse for this purple flip-flop, no change, and no change in this red flip-flop also. So what is the decimal equivalent of 101? That is 5. Now one more clock pulse. So it is changing from 1 to 0 back. Now complete pulse is provided to this purple flip-flop. So the output of this purple flip-flop is changed from 0 to 1. So this is half pulse for this red flip-flop. So no change with the output of this red flip-flop. So now 110, the decimal equivalent is 6. Now one more pulse. So what will happen? Again the output of this yellow flip-flop will change from 0 to 1. Okay. So by the help of this 3-bit digital counter, only decimal numbers from 0 to 7 can be counted. In case we want more numbers to be counted, more number of flip-flops can be applied in serial fashion. So in short, how it is counting? See, 1, 2, 3, 4, 5, 6, 7. Clock signals are arriving and then it is counting. So hope by this small lecture you would have learnt that how physically the digital counter works. Thank you.